The goal of this project was to design a propeller that would be tested in a wind tunnel. This propeller would be 3D printed and would have the goal of achieving 0.2 newtons of static thrust, being 0.1 newtons per blade, at 5,000 RPM and 0 meters per second incoming wind speed. Furthermore, at 5 meters per second incoming wind speed and 9,000 RPM, the goal was to achieve maximum efficiency. However, this propeller would only be designed using NACA 4-digit airfoils. In this video, you will find thrust and chord assumptions, an optimization algorithm to achieve the design goals mentioned previously, a validation model using CFD and various other software, a CAD model, and post-processing methods used after the 3D printing to ensure that the propeller will not break during testing, and finally results.
The way we settled for the thrust and chord distributions was the following. First, we considered an elliptical thrust distribution along the span-wise direction. To minimize the losses at the tip, we settled for the lowest thrust at the tip. However, there's a problem with this distribution, and that is that it demands too much thrust from the root locations, and since their tangential velocities are small, they would need very high angles of attack, or even the Reynolds numbers are too low, so this becomes an unfeasible design. What we instead settled for was a thrust distribution that would demand low thrusts at the root, still finite but low, and it would demand the largest thrust for the mid and 2/3 sections of the blade, and finally it would drop down to somewhere close to zero at the tip, again to minimize the losses at the tip. That gives us, in the end, something like this chord distribution, where the regions that demand the highest thrust correspond to the regions with the largest chords, so that they have high Reynolds numbers, and it's easier to get them to achieve high thrusts. And then as we move towards the root of the blade, we reduce the chord, and same for the tip. Since we're not demanding very high thrusts from this, we can also reduce the chord. This is, I believe, a second order function that gives us a nice smooth curve for this chord distribution. So the process with which we optimize the angles of attack at the different sections of the blade was the following. We defined errors in efficiency and thrust, and then we computed this objective function, which was going to be minimized, a cost function to be minimized. And what that means is that if we have a curve that depends on the angle of attack, a curve, let's say, for efficiency at the desired conditions, and a curve that shows the error in the thrust, what we want to aim for is to achieve the minimum error in both of them. However, we can see that if we achieve the minimum for only one of them, then the other one is really far away. What we were trying to do is, let's set an initial design and then move in both directions, see which one complies better with this equation, and then get through different steps, through several steps, to the condition that minimizes the error in both conditions. And that means that we get to some point somewhere in here, for example, at which both the efficiency and the thrust have the minimum error at both conditions, and that would be considered the optimal design. This is done for each of the sections of the blade, and we divided it in 8 sections. So we repeat this algorithm for each one of these span-wise locations, and in the end, once we put all of them together, we should achieve the best condition for the whole blade.
Once the optimal airfoil sections and cores were determined, the resulting propeller was analyzed using J-blade and star CCM J-Blade is open source software for propeller design and analysis using blade element momentum theory together with Xfoil for obtaining airfoil data and includes modeling of losses due to hub, tip, and 3D effects. Our propeller design was implemented in J-Blade and analyzed at the prescribed conditions of 9,000 RPM and 5 meters per second, predicting an efficiency of 26%. Since blade element momentum theory alone can't predict static thrust, we also performed a CFD simulation using star CCM, which gave us an estimated 0.179 newtons of static thrust at 5,000 RPM. Another simulation was performed at 9,000 RPM and 5 meters per second to give a second efficiency estimate of 34%. The CFD results also provided visualization of the flow distribution around the propeller and pressure distribution along the blades.
Alright, so this is the CAD model of the propeller. Here, as you can see, it has 8 airfoils, and they're all lined up using the half chord. So the airfoils in between were interpolated using SolidWorks' loft function, which used the leading edge and the trailing edge as guide curves. And finally, the hub was attached to the propeller by using a projected ellipse. The ellipse was made a little thicker than it should have been, just to make sure that the propeller wouldn't break during the testing.
The post-processing of the manufactured blade involves the removal of support material, the smoothing of the surface and removal of excess material, as well as balancing the propeller. While the wire cutters could be used far from the propeller itself to remove supporting material, extreme care must be taken when working near the propeller, especially at the trailing edge. Therefore, it is recommended to use a soldering iron to remove all the excess bits near the propeller. The received propeller is very brittle, with chips flying off, and a surface finish that is less than ideal. Therefore, it has been decided that it should be coated. Epoxy resin was used for this purpose. For the process of coating, you'll need resin, hardener, a cup, and some sort of mixing device. Pour resin into the cup and use at least 100 milliliters of it. Then, pour equal amounts of hardener or follow the instruction of your epoxy glue. Mix well and let it rest so that the bubbles float to the top. Use a cotton-covered stick to apply the resin onto the surface of your propeller. Keep spreading and pick one direction. We recommend the chordwise one until you have a smooth-looking surface. Give the glue 24 hours to dry and sand off any excess bits to get a smooth surface. Sometimes you may need more powerful tools. You can now use a prop balancer, or make one yourself like we did, to balance your propeller. Simply remove excess material using a Dremel or sandpaper on the heavier side of the propeller. A propeller is balanced when it keeps its horizontal position when placed on the balancer.
The propeller was attached to a motor and placed in a wind tunnel to assess the design's performance. A measurement of static thrust at 5,000 RPM was taken, and then the propeller was subjected to an incoming wind velocity of 5 meters per second for measurements of the thrust and torque to determine efficiency. The RPM was set between 4,000 and 15,000 in increments of 1,000 to determine the point of maximum efficiency. The resulting static thrust was 0.15 newtons, about a 17% difference from the expected value. The efficiency maxed out at 33% for 9,000 RPM, hitting the target RPM and matching well with the CFD results. The efficiency given by J-Blade significantly underestimates the actual value.
To finish, keep in mind that numerical models have different levels of accuracy. Implement a blunt trailing edge during your embodiment process. Make sure to melt off and not to cut the support material. Coat, sand, and Dremel to have a smooth surface. And finally, ensure that you have a large blade to hub attachment so that your propeller doesn't fail.